The greatest of human endeavors is a risky business.
Yeah, we've had a problem here.
NASA led the world into the exploration of space. But behind the scenes, out of the public eye, mistakes, mishaps, and failures plague the space industry.
Obviously a major malfunction.
Discover how NASA space failures further exploration. NASA wants to place humans on Mars. Plans for the roughly 35 million mile mission are in work. Because the Martian orbit around the Sun takes almost 2 years, a human mission to Mars is a 2-year commitment. But you can't just hop a rocket to Mars. Years of research and analysis have been completed, and efforts continue as NASA works toward the goal of placing humans on Mars by the year 2035. For the past 40 years, probes and then rovers have been investigating Mars, providing critical data. But it hasn't been easy. Mishaps and failures have threatened to derail NASA's efforts. In 1999, the $125 million Mars Climate Orbiter disintegrated because engineers did not convert English units of measure to metric units. A simple mistake that caused the spacecraft to think it was much farther from the planet's surface than it actually was. The result? It burned up in the atmosphere. Then, less than 3 months later, the Mars Polar Lander crashed on the surface of Mars because software incorrectly interpreted deployment of the landing gear as surface touchdown, resulting in the crash and complete loss of the mission, and the loss of another $120 million. NASA learned from their mistakes, refocused their efforts, and launched the Mars Exploration Rovers program. The program objective was to send 2 almost identical rovers named Spirit and Opportunity to investigate the surface of Mars. The 2 spacecraft would launch less than a month apart in 2003 in the critical orbital window when Mars was closest. If they did not make that window, NASA would have to wait another 2 years before launching the missions. And this time, with an $820 million budget, everything had to go right. So NASA constructed a surface system test bed called a Dynamic Test Model, or DTM. In NASA lingo, a MIR, SSTB, DTM. This MIR replica was created as an almost identical twin to Spirit and Opportunity. It carries many of the same electronics, hardware, research tools, and communications capabilities as a real rover. Many of the design specifications and functionality of the real MIR would be tested using the DTM. But as the launch date approached and engineers were testing a series of mission-critical procedures, a dangerous mishap occurred that once again threatened to derail the fragile trust NASA was rebuilding for its efforts to explore the Red Planet.
I was the test conductor that day. Next on the list was the high gain antenna pin puller. It was just another event.
In this particular case, we were operating basically in a nominal sense, and then we had standoff. The personnel standoff was what we felt at the time was an acceptable distance. We were following protocol.
We were just doing our standard sequence of, okay, is everybody ready? Do the countdown.
Are you ready for countdown? 5, 4, 3, 2, 1.
Engineers and technicians are stunned as fire and smoke confirm the failed test. Tense moments follow as everyone in the room realizes an unidentified object flew past them at a dangerous velocity. Fortunately, everyone is okay, and technicians quickly power down the DTM and secure the area.
Instead of the usual little pop, it was a big bang.
We weren't really sure what happened. There was just a loud explosion and parts flying around. The safety of the technicians actually was jeopardized. It was a close call, a very serious close call.
A close call that NASA would discover put the life and health of the technicians at risk. And beyond the safety concerns, the narrow launch window was bearing down on the engineering team. NASA needed answers, and fast. With launch day approaching and many more tests scheduled before the Mars Exploration Rovers could be cleared for launch, test engineers searched for answers.
If we are days or a week late in arriving at the launch pad, we may not be able to launch to Mars for another 2 years.
When the dangerous mishap occurred, technicians were conducting what is called a pyro shock test. Tiny explosive charges are used to deploy mechanisms during EDL, or entry, descent, and landing. A pyro shock test measures the amount of vibration or shock caused by the pyrotechnic explosion. Since MUR is loaded with sensitive research equipment, it is important to ensure the vibrations do not damage sensitive electronics or other hardware.
All of our spacecraft have multiple pyro mechanisms on them. They're involved in releases, separations, and deployments. One of the drawbacks to using pyrotechnics is the basic pyro shock, or the fact that they go bang. Some are fairly modest, some are actually quite energetic. The mechanism may be located adjacent to a sensitive piece of electronic equipment. What's the effect of this pyro mechanism on this piece of avionic equipment that's next to it or underneath it?
For the most part, pyro tests, even though maybe they sound bad, they typically are very boring.
But today's test was anything but boring. After the rover was secured, technicians began to discover the aftermath of the test failure. First, a deep gouge was observed in the camera mast surface. Something obviously had been shot out at a very high velocity and with substantial power. Damage to the wall behind the technicians confirmed that whatever shot out of the DTM had traveled dangerously close to the testing table and the technicians. Lying nearby, a small metal shaft was discovered. The shaft was identified as being part of a pyro mechanism called a pin puller. In fact, it was the piston from inside the pin puller used to release the high-gain communication antenna.
Basically, everybody in that room, if we would have been in the way of the pin puller, it wouldn't have been a good day for that person. That probably would have hurt, a lot.
As the MUR approaches Mars, NASA sends a final command for entry, descent, and landing. This command starts a series of events, including orbital insertion, parachute deployment, landing, and the process of unpacking the rover. Once this sequence is started, NASA cannot send commands to the spacecraft until all the automated steps are complete. After landing, one of the most critical operations is to deploy the high-gain communications antenna. It is a round, plate-shaped antenna and is the primary communications antenna. Researchers will depend on it for receiving commands, including telling the rover where to go, as well as uploading data and large high-res images of the Martian surface. It has the unique capability to turn and beam a signal directly to a receiving antenna on Earth, or relay its signal through orbiting spacecraft like Mars Odyssey and Mars Global Surveyor. A second low-power omnidirectional antenna is also aboard the MUR and sends signals in every direction, which is received by the deep space network of antennas on Earth, but its capabilities are vastly inferior to the high-gain antenna with slow data transfers and limited reception. If the high-gain antenna fails to deploy properly, MUR will not be able to fulfill its mission objectives. And if the low-gain antenna were to fail as well, there would be no way to communicate effectively with the MUR. This would result in a fully functioning rover that would never move again. Mission failure. The pin puller pyro shock test was extremely critical.
Turns out pin pullers are some of the highest shock sources. It's the most violent action. And so it causes a lot of shock, and for nearby hardware, whether it's a motor or something else, we have to make sure that the hardware survives.
Pyro pin puller consists of a housing, of a little pyro cartridge that actually provides the explosive force to drive the mechanism. There's a piston. The piston is engaged in the housing and protrudes from the front and is used to lock something in place. You fire the pyro cartridge, the gas pressure drives the piston back, releases the mechanism. After it releases, the piston slams against the cap, which is what produces the shock that we're concerned about.
The critical high-gain antenna is locked and held down by the pin puller. The piston secures the antenna in place. The pin puller housing contains two chambers filled with explosive charges. The charges are electronically activated. This creates a tremendous pressure buildup that moves the piston back against the cap, which creates the pyro shock. The antenna is released and then deploys, and if all goes according to plan, will begin sending information and receiving instructions from mission control and beamed the first high-resolution images from the surface of Mars. This pin puller test resulted in the piston lying on the floor. An inspection of the pin puller housing revealed that the cap had been blown off, allowing the piston to shoot out. Dozens of pyro tests had been conducted during MER processing, and NASA had no record of a similar incident. Engineers and technicians were starting to understand what happened, but needed to know how, and perhaps more importantly, why. If the high-gain antenna pin puller did not work on Mars, the $820 million mission could fail. When the pin puller failed, MER engineers were in the middle of an aggressive 6-day testing sequence. With many more tests to conduct and an unforgiving schedule, testing had to continue. The DTM was extensively inspected, and no other damage was found besides the gouge in the camera mast. Electronics were checked, and all systems were go.
They wanted to continue testing, so we implemented what we felt to be a very safe and secure methodology in that we put barriers up.
Plexiglass, basically shield in between the 1 or 2 people that had to stay in the room to conduct the test and the equipment under test.
As testing continued, engineers began to search for answers. Had the pin puller been installed incorrectly? Was there a design flaw or a flawed part? Were there other pin pullers already installed for this test schedule that would fail? Were the test parameters normal? Sometimes, hardware is tested beyond norms on the DTM to analyze hardware limits.
Sometimes we do more to the DTM, we kind of over-test it to help us have confidence in the flight hardware and keep us from maybe over-testing and risking breaking things on the flight hardware.
The investigation team confirmed the parameters for the test were normal, and no other previous tests in the area would have contributed to the failure. Next, the test processes and safety procedures were thoroughly reviewed.
And our procedures were reviewed multiple times by safety and other folks to assure that everything else was in place relative to safety hazards.
Data from the failed test was analyzed to determine if the voltage used to activate the pin puller was correct. The data indicated it was correct. Curiously, it also showed that the amount of shock when the piston made contact with the cap was also within normal levels. This meant that the pyrotechnic event, the small explosion, would not have produced enough force to damage the cap. This also proved that the pin puller would have been configured and loaded correctly prior to the test. So how did the piston break through the cap? As the mystery grew, the obvious suspect was the pin puller itself, but so far, nothing could explain the failure. Each pin puller is good for 4 tests. After each test, it is refurbished.
Which consists of taking it apart, cleaning it up, repositioning the piston in its engaged position, and then firing it again.
It was confirmed that the failed pin puller had only been used in 1 previous test, and therefore was not beyond the 4-test limit. Because it had functioned correctly before, a fundamental flaw in the basic design seemed impossible. The investigation team reviewed the purchase of pin pullers. An initial order was placed several months before testing began.
Did our series of tests and began to run out of hardware. So we went back to the vendor that we procured these things from, and they had 4. So we procured those 4 units and used those in a series of tests. We refurbished them for an additional 4 firings.
The failed pin puller was traced back to one of the 4 extra pin pullers that were purchased after the original group. The design specifications and the purchasing paperwork were reviewed. The design specs were the same. But a comparative analysis was about to reveal the source of the fiery test failure, initiating an aggressive response to ensure safety while NASA scrambles to meet the critical launch window before it's too late. With a narrow launch window approaching, the Mars Exploration Rover's Spirit and Opportunity are being tested using a fully operational replica called a dynamic test model. Any delay could result in the mission being pushed back for 2 years due to the proximity of Mars to Earth during orbital cycles. A critical communication antenna pyro test fails, leaving NASA scrambling for answers. The pin puller, which holds and releases the antenna, is traced back to 4 extra pin pullers that were purchased after the original group. After extensive analysis and side-by-side comparisons, NASA finally discovers the cause of the failure. All of the pin pullers, including 3 of the 4 newly purchased units, have steel caps, but the one pin puller that failed had an aluminum cap. Finally, a breakthrough.
With a steel cap, it appears that they're capable of 3 to 4 firings. With an aluminum cap, they're only safe to be fired once.
The pin puller had been used in one previous test successfully. It was refurbished and installed for the high-gain antenna test. But this time, when the pin puller charge was activated, forcing the piston back, the aluminum cap was too weak, and in an explosion of fire and smoke, the piston forced the cap off, shot out of the housing with extreme force, ricocheted off the camera mast, then flew dangerously across the room toward the test technicians. The aluminum cap was too weak to withstand multiple firings. This was confirmed when the cap was recovered from the test area. Space is a dangerous business, and although the direct cause of the failure was now known, the reason the cap was different had to be determined. When the pin puller fires on Mars, an unforgiving and alien environment, it must work. The investigation team begins meeting with suppliers and reviewing all purchasing activities.
When we went back and looked carefully at the design, it turned out that they had sold us units from 2 different lots.
The supplier of the pin pullers only had 3 extra pin pullers made with steel caps. In an effort to meet NASA's need quickly, they supplied a pin puller from a production run a couple of years earlier. Those were designed with the aluminum caps.
Not exactly a design flaw, but a design deficiency in that it had an aluminum cap. It fed it into an aluminum housing, as opposed to our design and the more recent other designs that had a steel cap that were much more robust.
When engineers created the specifications for the MER program, they did not communicate to the supplier that the pin pullers would be refurbished and used multiple times. From the supplier's perspective, the older unit with the aluminum cap met the required specifications. They saw no reason to communicate the difference in cap material.
It just happened that since we went back to 2 successive earlier designs, that we were not fully aware of it, and it wouldn't have been something that the vendor would have necessarily either acknowledged or known about or revealed to us. It wouldn't have, they don't assume that you're firing these things more than once.
But why wasn't the difference caught after the part arrived at NASA? Is it impossible to tell the difference between the aluminum and steel caps? And after the pin puller with the aluminum cap was used once, did it look any different than usual?
The signs of catastrophic wear are obvious if you're careful enough to look for it.
When the failed pin puller was examined, it was clear that the structural integrity of the hardware had been damaged prior to the failure. The threads of the cap were stripped. Why was this not noticed during the refurbishment process? The investigation team began looking into the process and criteria for refurbishment. They discovered that there was no defined process. Refurbishment was performed without any formal procedures, and the process was only known by the technicians who had been refurbishing the pyros for years.
It wasn't a particularly formal process up until this point. It was just something done by people who were familiar enough with it to do it.
The aluminum cap could have been identified at several checkpoints throughout the process, especially when it was damaged after the first test. But a lack of formalized procedures contributed to the dangerous test failure and a false sense of security.
The history was, nothing really ever goes wrong, quote unquote, with pyro tests.
When you're dealing with these kinds of mechanisms that sometimes appear quite benign, because some of them go, as I mentioned before, they go bang, and some of them just go click. So you can forget about the fact that you're actually dealing with explosives.
That might have maybe made some of us complacent or not so worried.
You need to be more careful.
NASA learns from its mistakes, but would changes to processes and safety procedures pay off? Launch day was almost here. A routine pyro shock test became a hazardous situation in less than 1 millisecond. A series of problems combined to form the perfect storm for the accident. NASA specs that did not clearly require steel caps. A supplier's failure to communicate the change in material. NASA's failure to communicate the pin pullers were refurbished and reused. A general complacency about pyro tests. And a refurbishment process that had no formal guidelines and therefore failed to look for signs of structural failure or material changes. Safety and procedural changes were implemented to ensure this kind of space mistake never happens again.
Any pyrotechnic testing is done remotely now. That's to protect the people, obviously, but also to protect critical hardware.
Where we actually have flight hardware or critical ground test hardware around, we have to get the refurbishment process witnessed by QA representatives. For less formal testing, we just have a checkoff procedure where we verify the integrity of the parts.
But would all the technical and safety changes, along with the improved open communication between all departments and suppliers, produce results? On June 10, 2003, Spirit lifted off and headed to Mars. Opportunity followed closely behind on July 7, 2003. The launch schedule had been met with little room to spare. For the next 7 months, NASA and the world wait as the spacecraft makes the 35-million-mile journey to the Red Planet.
Current altitude 8,000
On January
feet,
10,
moving at a
2004,
speed of 173
Mission
miles
Control
per
at
hour. We are
NASA's Jet
charged from
Propulsion
launch.
Laboratory sends the command for Spirit to begin
All
EDL.
systems are go for entry descent landing. We are roughly 11 minutes 48 seconds from landing at the Gusev crater in the southern hemisphere of Mars. Atmospheric entry in 3, 2, 1.
The spacecraft enters the atmosphere at 12,000 miles per hour, and within just 6 minutes will have to slow to 0 upon touchdown, except for low-frequency radio tones confirming certain EDL events.
Parachute detected.
Mission Control has no communication with Spirit until landing is complete. The first confirmation of landing will be sent about 14 minutes after touchdown. Then, after about 6 more minutes, if everything goes right, the signal will reach Earth and confirm Spirit rests safely on the surface of Mars. This was the moment, just under 5 years earlier, that Mission Control witnessed the destruction of both the Mars Climate Orbiter and the Mars Polar Lander. The atmosphere in Mission Control could not be more tense. Years, hundreds of millions of dollars, and people's careers are all invested in this moment.
Retro-rocket ignition has occurred. At this point in time, we should be on the ground. However, we currently do not have signal from the spacecraft. Deep Space Network tracking stations at Canberra and Goldstone are still searching for the primary signal. What do we see?
All systems confirm the landing has been a success. Then, 2.5 hours later, the world would see the first MER rover images from the surface of Mars. 21 days later, in a different remote location on Mars, Opportunity also lands successfully. The Mars Exploration Rover program will go down as one of the most successful planetary exploration programs in history. Combined, Spirit and Opportunity have sent back over 250,000 images of Mars, and Opportunity has traveled over 13 kilometers, breaking the distance record of any other space vehicle. NASA even named 2 asteroids after Spirit and Opportunity as their way of honoring the 2 now legendary robotic explorers. The mission was originally planned for just 90 days, but was given 5 mission extensions. Spirit remained operational and sending historic science data for 6 years, 2 months, and 19 days before losing contact March 22, 2010. Opportunity, however, has remained functional for an astonishing 13 years plus of scientific discovery on Mars. Only time will tell how much longer Opportunity will remain functional. Today, it is working with NASA's newest rover, Curiosity, searching for evidence of ancient life on Mars. Mir laid the foundation for successful programs like Curiosity and ultimately for placing humans on Mars. When exploring the unknown and pushing science beyond anything attempted before, space mistakes will happen, but the astronauts, technicians, and engineers who have dedicated themselves to exploring space will never let mistakes stop them. They innovate, fix the problems, and ultimately become better to go further and discover more.